Hello everyone, I'm Georgia Kudrika, and together with George Katsogiannis, we are here to walk you through the wonderful world of deep learning approaches for text-to-SQL systems. But first of all, let's ask ourselves why we need text-to-SQL systems in the first place. Nowadays, we are surrounded by data that are generated by users, systems, sensors, and so forth. And data repositories can now benefit more and different types of users that look for information, insights, patterns, and so forth. And as a benefit of data exploration has become increasingly more prominent these days. However, the volume and complexity of data make it difficult for most users to query data. And database query interfaces are well known for not being very user-friendly. Look here at this frustrated user trying to put together an SQL query to find what they're looking for. It would have been much easier if they could express their need in natural language, because what they're looking for is just which cities have year-round average temperature above 50 degrees. Is this text-to-SQL problem a new trend, a recent thing? Well, no, because already in 1974, people like Ted Code were saying that if we want to make the databases available to all users, then these users should be able to use their native languages when querying for data. Now, in this tutorial, we are going to have this agenda. First of all, we are going to talk about the text-to-SQL problems, see what challenges we have there, and then lay down the text-to-SQL landscape, talk about some early but notable efforts from especially from the database community. And then we are going to talk about benchmarks, and in particular, two of them that made possible the development of all these different deep learning techniques that we have, and we are going to discuss about today on for the text-to-SQL problem. We're going to talk about the natural language representation, essentially how we give natural language as input to such a system. And we are going to present a taxonomy that will help us understand better the systems, how they compare to each other, commonalities and differences. And then we have identified the most important text-to-SQL systems based on their contributions, their unique features, and we are going to discuss this. We're going to finish this tutorial discussing open challenges, and believe me, there are actually many, and look into the research opportunities that lie ahead of us. So let's start with discussing about the text-to-SQL problem. Essentially, the idea is that you have the user explaining what they want to see in natural language, and then the system translates the natural language question in the corresponding SQL query, executes this query, and generates the results and returns the results back to the user. So essentially, the user has this very nice interaction with the system that hides all the particularities of the underlying SQL queries that need to be formulated and executed, because the system takes responsibility to understand what the user is saying in natural language and find the right SQL queries to execute. Is this an easy problem? Actually, no. We have many challenges, both from the natural language side as well as the SQL side. What type of natural language challenges we have? Well, natural language is complex by definition, so we're dealing with things such as ambiguity. When we say show information about Paris, do we mean the city? Do we mean the person? When we say model, does it refer to the car model in the database or the engine model? So how our natural language elements link to the schema elements. And then what about information that is missing but implied in our query? For example, when we say the president before Obama, the system should understand that we're talking about the US presidents. And then, of course, you have user mistakes that add additional complexity on top of everything. When you have, for example, spelling mistakes or syntactical and grammatical mistakes, how does the system figure this out and understand what the user really meant? From the SQL side, things are not much easier because SQL is a structured language with strict grammar, limited expressivity. So even if something is quite simple to explain in natural language, for example, which countries have a GDP higher than the EU average, That may require a very complex, a convoluted SQL query with nesting and so forth. Then the database structure puts additional obstacles because the user's data model may not actually match how the data are stored, the data schema. For example, when we say find directors who released the movie this year, that could actually imply that we need to join many different tables in our database in order to connect directors and movies. Now let's see some of the approaches that exist there and try to sketch the text to SQL landscape. Now, if we want to see at a high level how a system for a text to SQL solution would look like, essentially we can distinguish the following components. So we have the parser that takes the SQL, the natural language query, and tries to find which terms and phrases are important for processing. And then the entity mapper takes these terms and phrases and tries to map them to the underlying database using inverted indexes, sometimes using external knowledge bases, and so forth. Then the interpretation generator is responsible for finding what the user means. So taking the schema elements, the database elements that were identified, and finding how they should be connected in order to bring back the results that the initial NL query is describing. And since we have ambiguity and since we have all these issues that I already mentioned, all these challenges, the system may actually generate more than one interpretation and rank them, and then send them to the SQL translator that is responsible for producing the actual SQL code that will be executed and bring results back to the user. Now, let's see some early generations of text-to-SQL systems. Initially, we have keyword systems that expose a search engine-like functionality, where essentially user queries contain just keywords, like drama movies. And here we have some notable early systems that we distinguish here for their contributions. So Discover was the first to introduce the idea of generating query interpretations as subgraphs over the database schema graph. Then Discover IR said, why not using information retrieval style ranking to enhance the query disambiguation process? Spark was a system that built on top of that, but also focused on fast execution methods. Then we have what we call the enhanced keyword systems, where here we have queries that are richer because now they can support aggregate functions, group by, comparison operators, and also include keywords that refer to the database metadata. This type of system also have syntactic constraints on the input. For example, a query would be like count movies actress Priyanka Chopra, and by having this specific syntax, they make sure that they can parse the user query. And here we distinguish ExpressQ, that was actually the first one to have keywords that trigger aggregate functions and group by clauses, and then so that enrich the system knowledge, that is the inverted indexes that are used to find how NL elements refer to database elements with additional knowledge sources. Then, of course, we have natural language systems that essentially allow queries in natural language, like what is the number of movies of Priyanka Chopra? And here, of course, we have Nalir that introduced a syntactic parser to understand the natural language question, and Athena that introduced the idea of using ontologies and ontology data mappings for essentially handling the problem of how you map the user data model to the actual data schema. Now, let's have a look at a specific example using our high-level architecture here. And the example that we're going to see is actually how Nalir would execute this query, would translate this query. So our query here says what movies have the same director as Revolutionary Road. And then the parser, that is now the Stanford syntactic parser, would take this and generate a syntactic tree that tells us how the different parts of the query relate to each other syntactically. Then this tree will be given to the entity mapper that will try to find how the various parts are found within the database. So here we see that Revolutionary Road is in fact the value of movie title, and movies and director correspond to these specific tables in our database. Then the interpretation generator will generate an intermediate tree that captures how these database elements should be connected in order to generate the results. And now this is something that the system understands in order to use it by the SQL translator and generate the code that is needed in order to bring back the results. Now, one thing that I want us to notice here is that this SQL code does not, of course, comprise the exact SQL query that we would expect to match our initial NL query. And this is something different that we see in systems that have been developed by the database community, because they really care not only about the effectiveness of translation, finding the right SQL query for the NL question we are asking, but they also care about the efficiency of the execution. In deep learning approaches that we are going to see, the problem is just finding the right SQL query, and that actually allows us to compare the different systems using a common benchmark. However, here it would have been much more difficult. Now, the last few years, we see many different systems that employ deep learning techniques for the text-to-SQL system. And these systems will actually see the text-to-SQL problem as a neural machine translation problem, where they train over a large body of NL and SQL pairs. And when they see a new natural language question, they try to figure out what is the SQL query that should be mapped to this natural language question. Now, at this point, it is necessary to talk about benchmarks. And in order to do this, we have to discuss about evaluation of text-to-SQL systems, that the way that it was done for several years. And there are several shortcomings, several pain points that we have identified here. And no common data set, so different system evaluations would use different data sets of different complexity. These data sets are usually proprietary or small ones. Most importantly, no standard query sets would be used, and each system may use a different query set, small query set, and all these conditions essentially do not allow us to have a clear idea of how different systems compare to each other. And an additional problem is that when they do, and whenever they do effectiveness evaluations, they use different methods. They could use a user study, they could do a manual evaluation. Some of them could compare to some gold standard queries and so forth. Now, this has changed with two new benchmarks that we're going to discuss in a minute that actually provided pairs of NL and SQL queries, and made, of course, possible the development of the deep learning techniques for text-to-SQL systems. Now, let's take a look at each one of those in more detail. So the WikiSQL benchmark is a large crowdsourced dataset for developing NL interfaces for relational datasets, and it has around 80,000 pairs, NL to SQL pairs, over 25,000 tables that are gathered from Wikipedia. Now, one thing to notice here is that these questions are over single tables, not entire databases. That's why they're quite simple. So for starters, they don't have joins. The other issue with WikiSQL is that it contains many mistakes. And we're going to see how these mistakes actually have been generated. Now let's see an example. So here we have this table that has been extracted from Wikipedia, and we see a pair of an NL query and the corresponding SQL query. And this is actually a good pair. what nationality is the player Maxi Bugs. Now let's see a bad example. So here we have the original wiki table, but now here is the wiki SQL table as was extracted and copied within the dataset. And we can see that the extraction is not very good. And as a result, the SQL query is not meaningful. And of course, the NL query is not meaningful either. So this irrelevant pair here is a bad example that cannot actually be used to train a deep learning system or to evaluate an approach. Now, Spider solves this problem because it was annotated manually by 11 Yale students. It is a smaller dataset containing only 10,000 questions. It has questions over 200 databases from around 138 different domains. And these queries are divided into 4 categories: easy, medium, hard, and extra hard. So the queries that we have here have much better quality and more diverse complexity than the queries that we see in WikiSQL. Let's see some examples. So here we see an example from the easy category, and we can see that it just contains one table and, for example, just a count. Now, an example of a medium complexity query has a join and a group by. And then a hard query has a lot of joins, group by, having, and then at the last category, the more complicated queries are queries that may have, for example, nested subqueries.
So now that we have familiarized ourselves with the problem and the data, we can start looking into how a text-to-SQL system is built. The first and a very important part for any system is the way that we choose to represent and handle natural language. The main problem here is that neural networks can only accept numerical inputs, so we must find a way to transform the text into numbers. The standard way that this was done until very recently was by using some word embeddings technique, whether that is the more primitive one-hot embeddings or a more advanced representation like word2vec or glove. And we would give these word embeddings to a recurrent neural network, such as an LSTM neural network. However, since the introduction of the transformer neural architecture, we are currently seeing the rise of language models such as BERT, that I'm sure almost all of you already know, and even more advanced variations like Roberta that keep coming up. And we can even see some language models that have been trained specifically for handling tabular data that can be very useful for the text-to-SQL problem. So first of all, let's take a look at glove embeddings. The idea here is to create meaningful vector representations for all the words in our vocabulary. And the way that this is done is by performing unsupervised learning based on word co-occurrence in the training corpus. And what glove achieves is to create very useful linear substructures in the created vector space that show the relations between the words. So in this example, we can see that the distances between the words man and woman will be similar to the words sir and madam. Additionally, using glove, it is very easy to find semantical near neighbors, so it can be used for even other tasks like word similarity and so on. And the way that we would go about using gloves is that we can download a pre-trained set of vectors from Stanford's website that has been trained on a large corpus like Wikipedia, Twitter, and so on. Now, the main problem with approaches like glove and word2vec is that they operate on a fixed word vocabulary. And since the memory we have is limited, so is the size of the vocabulary. And inevitably, there will be some words that will be out of this vocabulary. To avoid this, word piece embeddings propose using subword units so that we can split unknown words into smaller known subwords. And the way this is achieved is we start again with a large training corpus, and we decide from the start how big our vocabulary is going to be. So the algorithm initializes itself with the vocabulary containing all unique characters. So essentially all letters of the alphabet, all single numbers, punctuation marks, and so on. And at each iteration, more tokens are added to the vocabulary by combining single characters while trying to minimize the number of words that are needed to segment or to tokenize, if you like, the training corpus. Obviously subject to the vocabulary size that we have decided from the start. And here we can see a comparison of these two representations. And as you can see, Glove will fail to assign any vector to the words Mugsy and Bogues. And this is expected because it's a very rare name and we cannot expect from Glove to have it in its vocabulary. So it will be forced to assign maybe a zero vector or some other vector that we have decided to assign to all unknown words. However, WordPiece will be able to split these two unknown words into smaller known subwords, so there will not be any unknown vector that essentially will be garbage for our model. So now let's take a look at BERT. BERT essentially is a very large pre-trained neural network. The base version of BERT has 110 million parameters, and it can be applied on a very wide variety of natural language tasks by just stacking some task-specific layers on top of BERT and performing extra training, which we call fine-tuning, on the specific task that we want to solve. And in fact, the authors of BERT show at their initial paper that BERT can achieve state-of-the-art results at a wide variety of natural language tasks by using very simple linear layers on top of BERT. So a few things about BERT's architecture. It takes as input a sequence of WordPiece embeddings. It processes them using many stacks of bidirectional transformer encoder layers, and it produces an output of equal length that we call contextualized embeddings, because they have information about not just themselves, but also all the other tokens in the sequence. And the way that we pre-train BERT is that we use a very large text corpus of almost 3.3 billion words, and we pre-train it simultaneously on two different tasks. The first task is the masked language modeling task, on which we mask out certain words and we ask BERT to predict which word is missing. And the second task is the next sentence prediction task, on which, given two sentences, BERT must decide if the second sentence is the next sentence. So in this example, we can see, first of all, how the input is structured for BERT. We always start with a CLS token that is used for classification tasks, like for the next sentence prediction task. Then we give it the first sentence. We mark the ending of the first sentence with a separating token. Then we give it the second sentence, and again we mark the ending of the second sentence with a separating token. So in this example, we would use the output of the classification token. We would give it to a linear network, and this network would predict if sentence B is the next sentence. So in the example, the man went to the store, he bought a gallon of milk, so it is in fact the next sentence. And we would also mask out certain tokens of these sentences, and we would use the outputs of the masked tokens. We would give them to linear networks that would predict which of all the words in the vocabulary has been masked out. And when we have a pre-trained version of BERT, we can fine-tune it on the task that we want to solve. And essentially, this is an application of transfer learning because we have a very large model that is trained on a very general natural language task. And what we do is we add some extra layers and perform additional training on our task. And this allows us to achieve much better results. And what we have to do pretty much is we have to make two decisions. The first decision is how we're going to structure our input and how we're going to give it to BERT. So in this example, let's say we have the Wiki SQL dataset. We could say that instead of the first sentence, we're going to give the natural language query. And instead of the second sentence, we're going to give some information about a column in the table. And we also have to decide how we're going to use BERT's output to make predictions for the task that we want to solve. So let's say, for example, we could use the output of the classification token to decide which aggregation function will appear in the select clause. So this is a classification task out of a standard set of options. And as I mentioned earlier, there's a lot of variations of language models, and some models have been pre-trained specifically to handle tabular data. And Grappa is such an example. It is initialized by Roberta Large, which is a language model very similar to BERT. It has two main differences. It is larger, it has more parameters, and it is pre-trained with a different choices of hyperparameters, which its creators show that achieves better results this way. So Grappa is initialized by this language model. It uses synthetic pre-training data, which is created from a choice of various tabular datasets like Spider, Wiki SQL, Wiki table questions, which is very similar to Wiki SQL, and other datasets containing tables and descriptions about these tables. And the two pre-training tasks for Grappa is first the masked language modeling task again, but this time we're not giving two sentences from a text corpus. Instead, we're giving natural language queries or table descriptions along with the table and the columns that they are directed to. And the network must now predict missing words from a natural language query and table columns. So this gives it a better idea about the specifics of a table and the natural language query. The second task is called the SQL semantic prediction task, in which we give an input of a natural language query and a set of table columns. And for each column of the table, the network must predict if this column is going to appear in the SQL query that is equivalent to the natural language query, and what its role will be in this SQL query. So will it appear in the select clause? Will it appear in the group by clause? And so on. And experiments show that when we simply replace BERT or Roberta with Grappa, systems show better performance in the text to SQL tasks. So this goes to show that even by changing the way we process natural language and without delving deeper into the system, we can achieve better performance because the way we handle natural language is very important.
Let us now discuss the taxonomy for text-to-SQL deep learning techniques that is also going to help us understand the differences and commonalities of the different text-to-SQL systems that we're going to present. And we distinguish three main dimensions: schema linking, that tells us how to connect query elements to database elements; input encoding, that tells us how we should give us input the natural language question and the database information, the database schema information. And last but not least, the decoder output, whether it is a sequence, a sketch, or a grammar. So let's start with schema linking. The problem here is how we can discover links between the various query elements and table, column, and values that exist in the database. So essentially, we distinguish 3 different types of possible schema links. Now, let's take as an example the natural language question that we have here: how many heads of the departments are older than 56? That is expressed over our database here that has 3 tables: department, management, and head. Now, let us first discuss about different possible links that we can find in this particular example, and see whether how some of them are indeed correct and useful, and some other create more problems than they actually solve. So an easy case is heads here, which is very easily mapped to the underlying table head. This is a table link, and it's actually a correct one that will help us translate the query. A similar case is with 56 here, when we are able to map it as a value to the age attribute of this table here. Now, let's see a totally different case. So we have the departments here who that in principle would be very easily mapped to the underlying table department here. However, this particular table link is not correct, because in the context of our query, we do not care about departments, we care about the heads of the departments, and this is actually already captured by the table link head. Now, let's look at other possible mappings or links for the value 56 here. So it is a numerical value, and it could be also linked to, let's say, head ID and department ID, but these value links do not provide any value. In fact, they will hurt the translation process because they create more ambiguity. Now, we have a plethora of techniques to perform schema linking, and database lookup is one that we have already discussed in the first part of our tutorial when we're discussing about the early database approaches for the text-to-SQL problem, where inverted indexes were used in order to map elements from the query to underlying tables, attributes, and values. But here we're also going to discuss about other approaches in more detail. Of course, as we're going to see when we're discussing particular examples of text-to-SQL systems, some of them actually do not use any special schema linking technique. They rather have the neural network that is responsible for the translation to figure out implicitly schema linking, and do not perform anything else in addition to that. So let us talk about some specific schema linking techniques. And for the purpose of our discussion now, we are using a different example. So we have 2 queries. For each department, show the budget in billions, and show all department directors from New York. Now, we have different cases of schema linking that require different approaches. Let's take an example here, the department. The department is actually a case of an exact match, and that can be just very easily mapped to the underlying table department through a simple index, for example. Then we have the case of budget in billions, where we have essentially a phrase that needs to be mapped to the underlying database schema. And for this particular case, we see that an anagram search would be a more appropriate technique. Then we have department directors, which is even more complicated, because now department directors actually should be mapped to head. And if we don't have any additional knowledge, that mapping is not obvious how we could do it. So in the case where we do not have exact matches between query elements and database schema elements, approaches that are appropriate for this problem is n-gram search, use of similarity metrics, heuristics, or even external databases, for example, or knowledge base, for example, WordNet is a very popular example. Now, what about linking parts of the query with values in our data? Now, of course, one approach is, as we already discussed, using inverted index. So take a look here at New York. So we could use an inverted index. And again, here we may need to look using an n-gram search. But it may also be the case that either because our data does not match exactly what we see in the query, or even because the data is not accessible, for example, due to privacy issues, an external knowledge base may be more appropriate. So essentially here we have two possible approaches, using an inverted index for creating these data value links and using knowledge graphs or other external sources to make these connections. Another approach would be to use a special purpose neural network, a classifier essentially, to find such potential links. And we're going to use, and we're going to discuss some particular examples of systems that use such techniques to find, for example, that some parts of the query are of string type, or some parts of the query are talking about people, and so forth. Now let's move on to the second dimension for taxonomy, input encoding. Essentially, the question here is, how can we structure the input for the neural network? And we need to give us input the natural language question and also information about the underlying table that this question refers to. So here we have essentially four different possibilities. The first possibility is to use two different encoders, one for the natural language question and another one for the column tables of the database. Now, the second approach is to do exactly the opposite. So concatenate the question with the information about the database schema and give this input to a common encoder. Now, another approach that we're going to see is to essentially do something in between the two other approaches and encode the NL question with each column separately and feed this into a common encoder, one after the other. Now, the last and more sophisticated option is to try to encode the whole schema graph. And as we're going to see, this is the richer approach that we have now in our hands. So let's start with the option of doing separate encoding. So this was an approach that was used by the first text-to-SQL systems, SEC2SQL, SQLnet, and these were used over WikiSQL that, as we remember, has only questions over single tables, not whole databases. Now, why do we need to do separate encoding? Now, a natural language question is mapped is viewed as a sequence of words. Now, the column names, each column is a sequence of words. Hence, all the columns names together is a sequence of sequences of words. So, in order to be able to encode these different representations, we need two different encoders. And then, of course, at the next step, the two different inputs must be combined. For example, using attention, using concatenation, and so forth. Now, let's go to the second option. Instead of doing all this separately, let's put them together in one common input and give this to a common encoder. Now, this option is actually widely used by newer systems that use language models. And here we don't need, of course, to combine different inputs because that has been taken care of very early. And if, for example, we go back to our example with department management and head, this database, and let's say that the question is still our well-known example of how many heads of the departments are older than 56, then this question and the database schema are given as input in a format like this, where we have, first of all, the tokens of the NL query, then we have a separator, and then we give the database schema, each column, one after the other. And notice here how the database schema is essentially flattened. So we don't see the tables, the connections between the tables. We just have the columns that exist in the database. And of course, we have again the separator to show where each column, wherever we have a new column. Now, a third option that was actually introduced and used by HydroNet, as we're going to see later on, is to encode the natural language question separately with each column. Now, the reason that this is happening is that because HydroNet essentially views the problem of predicting which column should be used for a particular query as a prediction problem or as a classification problem, and encoding them like this helps essentially this problem formulation. Now, this also works very well over WikiSQL. HydroNet was developed for WikiSQL, and we haven't seen any similar approach that works for Spider, that essentially works for multiple table databases. Now, the latest and the most elaborate approach is, of course, to try to encode the whole schema graph. Using graphs essentially allows us to preserve all the schema relations that we have. For example, which columns belong to which table, which columns are our keys, how our tables are connected through joins, and so forth. Now, the words of the natural language question can be added over the database schema graph based on schema links and similarity hints. For example, in what we have here, we see that we have the different tables, how they connect through different columns, and then we see in pink the different parts of the query and how these parts may be mapped, may be linked to particular elements of the database. For example, here we have Q3 that is linked to this particular table in our database. Now, the last dimension is has to do with decoder output. And here we distinguish three main categories of text-to-SQL systems: sequence-based, grammar-based, and sketch-based. Now, sequence-based approaches were actually the earliest approaches that we see in text-to-SQL deep learning techniques, where essentially the natural language question is an input sequence, and the system generates an output sequence that is now the SQL query. So essentially here, the problem is a sequence-to-sequence transformation problem, and we train our network to learn to generate from one sequence of tokens, that is the input, another sequence of token that is the output. Of course, that has the obvious benefit that it simplifies the text-to-SQL problem, but is also prone to many issues. First of all, treating the problem as a sequence-to-sequence, nothing stops the neural network from creating syntactical errors when generating the SQL query. Hence, the query may not be even executable. And that is actually the reason that these approaches are not used anymore in recent works. So we have them only, for example, in Sec2SQL, that was an early system for text-to-SQL translation. Now, the sketch-based approaches are essentially built on the shortcomings of the previous approaches. So in order to avoid the syntactical errors that we saw in sequence-to-sequence translations, In this approach, we say, okay, we can have a sketch of the query. The missing parts of the query become slots that needs to be filled. And here we have an example of such a sketch from the SQLnet system, where we see that we have select where, and as slots, we have an aggregate, a column for the select part, and the where clause has conditions in this form, and and also combinations of conditions are allowed. Now, what are the pros and the cons of this method? Of course, the simplicity is again an advantage, because now following this divide and conquer approach, we are simplifying the whole problem because we divide the task into smaller subtasks. So instead of trying to figure out the whole query, we need to figure out the aggregate. We need to figure out what is the condition and so forth. But as we are going to see, many of these systems use very complicated neural networks. It's part of the neural network being essentially one dedicated network trying to figure out what should be put in a specific slot of our sketch here. And that is why essentially these approaches are hard to extend to complex queries. Now, the grammar-based approaches essentially try to handle these previous shortcomings, and instead of trying, and they try instead to generate a sequence of rules, a grammar, instead of simple tokens, that can be used to generate an SQL query. And as we're going to see, several approaches, more recent approaches like IRNet and RATSQL are actually grammar-based approaches. And here we have clear benefits. The approach makes it much easier to avoid errors. They can more easily cover more complex queries, but of course, they are more sophisticated, and that requires a more complex design for the actual neural network that is used for the translation. And now we need to discuss one last thing that has to do with execution-guided decoding. Now, as we saw, sketch-based approaches are very good at reducing at least the possibility of errors, but errors still can happen in the output. For example, there may be a mismatch in the aggregation function or a mismatch in a condition type. For example, we may try to compare a float type column with a string type value. So the idea of execution-guided decoding came as an extra step to help the system avoid making such choices during prediction time. Essentially, what is happening here, the main idea is that the system executes partially complete predicted SQL queries and tries to figure out which of these cannot be executed and reject them if the system finds that there are execution errors or these queries will yield empty results. Now, one last remark that we need to take into consideration here is that the approaches that we have seen from the database community actually never have this problem, because they always figure out and translate the NL query to a correct, a syntactically correct SQL query and semantically correct. And so they don't have to do this extra step. And another thing to have in our mind here is that this execution-guided decoding adds extra processing time during the translation that current deep learning techniques that are using this approach do not really consider, because they do not evaluate their execution times. Their evaluations only focus on effectiveness of the system, how many queries it can translate correctly. So at this point, we are ready to talk about text-to-SQL systems.
So now that we have seen all the main aspects of the text-to-SQL system, we can start looking into some actual systems and see how they chose to implement each of these parts. Sec2SQL was the first neural text-to-SQL system to be proposed, and it was proposed along with the WikiSQL dataset. It uses glove embeddings for natural language representation, and it uses two separate encoders, one for the natural language query and another for the table columns. Then the encoded representations are given to three separate subnetworks, each of which is responsible for predicting a different part of the SQL query. So we have one network that predicts which aggregation function is going to be used, a second network that predicts which of the table columns will appear in the select clause, and a fourth network that is responsible for predicting the entire where clause. And this particular network has a sequence-to-sequence architecture, and this is the reason why we say that Sec2SQL has a sequence-based decoder. And this is also the reason why a lot of errors can occur, because this exact network is responsible with predicting a syntactically correct order for the words it's going to predict. It has to predict SQL keywords, operations, and so on. So it has all the disadvantages of a sequence-based decoder that we have already discussed. And to tackle this exact problem, SQLnet was proposed, along with the sketch that you can see here on the bottom right. And what it achieved with this sketch is to have a completely sketch-based decoder and to avoid all the drawbacks that we saw earlier. So the way it achieved this is by splitting the network that was responsible for predicting the where clause into four different subnetworks that are responsible for different parts of the where clause. So it has a network that is going to predict how many conditions will appear in the where clause, another network that is going to predict which columns will appear in the conditions of the where clause, another network is going to predict the operations for each column, and the fourth network that is going to predict the values for each condition. And this last network is also a sequence-based network. However, the big difference here is that it is only responsible for predicting the values. So it does not have to predict a syntactically correct order. It does not have to predict any keywords and so on. So the worst thing that can happen is a column type mismatch. So if we have integer type column and a string type value, this is going to result in a query that is not executable, but this is the worst case scenario and it can be avoided with execution guided decoding. Some other features is that now each of the networks in SQLnet has its own pair of encoders, and it also introduced the column attention mechanism, which essentially is a neural module inside each of these networks that tries to emphasize words in the natural language query, given the names of the column of the table. So this is maybe an initial hint towards schema linking. However, this is all inside the network, so it is not done before giving the input to the network and maybe trying to help it process the input better. HydroNet is another sketch-based system working on WikiSQL. What is very interesting is that it almost completely relies on BERT, and besides BERT, it uses very simple linear networks to make predictions for each slot of the sketch. And another interesting feature is that it processes each column of the table separately and makes predictions for each one of them separately. So let's see exactly how this is done. For each column of the table, we're going to construct a different input for BERT, and this input is going to contain the natural language query, of course, and the type of the column we're processing, the name of the table, and the name of the column. We're going to give this sequence to BERT, of course, using the CLS token at the beginning and the separating token between the NLQ and the information about the column. And then we will use the output of the classification token to make some predictions, like, for example, if the column we're processing at the moment is going to appear in the select clause, and if it does, what kind of aggregation function we're going to use, if this column will appear in the where clause, and what kind of operator will be present. And all these predictions are made using simple linear networks and an activation function like a sigmoid or a softmax. And finally, if we decide that this column is going to appear in the where clause, we also have to find a condition value. And to do this, we're going to iterate through all the outputs of the NLQ tokens. And we're going to give each one of them to two networks, one that predicts if this is the start of the value and another that predicts if this is the end of the value. And both these networks are, again, very simple linear networks. And by doing this, we can also discover the span of the value, and we have a way to construct the SQL query. SQLova also works on the Wiki SQL dataset. It is also sketch-based, using the same sketch as SQLnet. And as you might see, this top part is very similar to SQLnet. In fact, it is almost identical. The main difference from SQLnet is that SQLova uses BERT, and it concatenates the natural language query and the table columns. It gives this input to BERT, and then it uses this output to a very complex network that is essentially SQLnet. So we could say that SQLova is like SQLnet, but with BERT instead of glove embeddings. And obviously, this network achieves better performance than SQLnet due to BERT's better capabilities of handling natural language. However, what is very interesting is that it does not achieve better accuracy than HydroNet, which is much simpler. It only uses linear networks, and this might go to show that when we're using BERT, it might be better to follow the way that it was pre-trained. So it might be better to use simple networks, use the CLS tokens output for classification tasks, and so on. So SDSQL is the last system that we're going to see today that works on the Wiki SQL dataset. If you look at this figure on the top right, this part is almost exactly the same as SQLova. The main difference is this network, which is responsible for schema dependency prediction. And what this means is that it tries to find schema dependencies between the words of the natural language query and the columns of the table. So, for example, one type of dependency is the select column dependency. And in this example, we can see that the word nationality has a select column dependency to the column nationality, because this exact word signifies that the column nationality will appear in the select clause. So this schema dependency task essentially is a version of schema linking that is done inside the network. And what is very interesting is that even though the predictions of this task, the schema dependency predictions, are not used to construct an SQL query, but what is done is that by learning both the SQL prediction task and the schema dependency task at the same time, SDSQL is able to optimize itself better for both tasks and actually achieve better accuracy when predicting SQL queries than any of the systems we have seen so far. So now let's see some systems that work on the spider dataset. So we're going to expect from them to have better expressiveness and be able to create much more complex SQL queries. So we're going to start with IronNet. And first, we're going to see how IronNet handles schema linking. So the first step in IronNet is to consider all n-grams of length from 1 to 6 in the natural language query. And IronNet is going to try to match all the possible n-grams to either a table name or to a column name, either an exact match or a partial match. So you can see, for example, that the word department is matched to the table name department here. And for value linking, what IronNet does is that it considers all n-grams inside quotes as value links. And what it has to do now, it has to decide to which column of the database this link is pointing. So IronNet assumes that we do not have access to the values of the database, which might be a real-life scenario, maybe due to privacy issues. So in order to tackle this problem, IronNet does something very interesting. It searches these value links to a knowledge graph called ConceptNet, and it takes the results that ConceptNet gives and tries to match these results to a column. So you can see in this example, we have New York, which is inside quotes and has been marked as a value link. And if we search New York in ConceptNet, we will get the result that New York is a state. So we can then search state in the database schema, and we can match it to the column born state in the table head. So having discovered some links from the natural language query, we can then move on to encoding the input. IronNet can use both GLOV or BERT, but obviously accuracy with BERT is higher, so we're going to see the BERT variation here. So what IronNet does is it concatenates the natural language query and the table and column names. And it also adds some schema linking tokens to all the spans that have been linked to a schema element. So for example, it has this table token for the word department, and it has this value token for the bigram New York. And it gives this input to BERT, and BERT is going to produce an output of the same length. And IronNet takes an extra step here, and it processes all spans that have more than one tokens using LSTM networks to reduce them into single tokens. So for example, New York has two words, and it also has a value token. So it's going to take these three tokens, give them to an LSTM to get a single representation for this span. And for the table columns, it does a slightly different process where it adds an embedding type vector to each column to signify what its type is. So it can be of integer type, of string type, and so on. So this is a way to try to preserve more information from the schema in the representation that we create. And finally, having created this representation of the NLQ and the schema, IronNet moves on to decoding. It uses a grammar-based decoder, and the authors of IronNet have designed a specific intermediate language called SEMQL that they argue it is better to predict in SEMQL instead of SQL. And the way that they predict SEMQL is by predicting an abstract syntax tree of SEMQL using an LSTM-based decoder that at each step predicts a rule. And if we apply these rules Sequentially, we can construct a SQL abstract syntax tree, which we can then transform deterministically into an SQL query. And another very interesting feature of IronNet is that when it wants to predict a table or a column name inside this abstract syntax tree, it can make a decision to either pick a column or a table name from all the available options in the schema, or it can choose to make a choice from memory, which is all the table and column names that have already been generated in the current query. And this is very useful if we think, for example, when we generate a having clause, we're going to want to use a column that is already present in the query and not a new one that we haven't used yet. Moving on, ValueNet is another system that works on the spider dataset, and it is very similar to IronNet. What its main difference is and where it improves IronNet is on predicting better condition values. And we have not stressed this out too much, but most systems that work on the spider dataset are not that good at predicting condition values. And in fact, the leaderboard of all the systems working on IronNet does not take into account their ability to predict correct condition values. And the reason for this is that when we are predicting a table or a column name, it is very easy to make a decision because we have a fixed set of options that we can choose from. However, when we want to predict a condition value, besides looking at all the words of the natural language query, it is not possible to look into the database and assume that these are all our options and make a decision out of this, because the variety of choices will be huge and we cannot handle this. So what ValueNet does is it adds value candidates to the input so that the system can choose, can have a set of choices instead of trying to guess. And the way that this is done is by a process, an extended value candidate discovery process. So the first step is value extraction using named entity recognition and heuristics. So we try to extract values from the natural language query. So in this example, we could say that using named entity recognition, we're going to recognize New York. Then the next step is value candidate generation that happens using string manipulation and by looking for similar values in the database. So let's consider in this example that the value stored in the database is NY, just the acronym, and not New York. So ValueNet is going to manipulate this string, look it up in the database, and it's going to find one candidate that is going to be NY. And the final step is to validate all the value candidates because it's going to produce a lot of candidates. So to eliminate some of them, it's going to look them up in the database, and if they do not appear in the database, they're going to be thrown away. But this value NY is going to appear in the database, so it is going to stay. And finally, it is going to encode all these inputs by concatenating the NLQ, table names, column names, and finally these discovered value candidates. So ValueNet is going to have this exact value NY in its input. So it's going to be much easier for ValueNet to predict the correct condition value for this query. So Bridge is another system that works on Spider. What is very interesting about Bridge is that it has a sequence-based decoder besides all the drawbacks that we have discussed. So we're going to see how it manages to maybe handle these drawbacks. So first of all, it uses BERT for natural language representation. It concatenates the NLQ with the table and column names. And for schema linking, it only does string matching against pick lists of the database. So essentially, it only does value linking. And this is a bit similar to ValueNet, but much more simple because it is going to concatenate all the discovered values at the end after all the table and the column names. So it encodes this input using BERT and using bidirectional LSTMs, and also it uses some metadata information from the schema like column types and foreign or primary keys to try to preserve some information for the system. And then it uses an LSTM decoder, a sequence-based decoder, that at each step is going to perform one of three actions. It is either going to generate a token from the vocabulary, it can generate a token from the natural language query or from the schema. And this vocabulary that I mentioned can include words like SQL keywords, operators, and so on. So the first thing it does to tackle the drawbacks of a sequence-based decoder is to transform all SQL queries into execution order. So instead of having select, from, and where, it's going to change the order to always start with the from clause, and then the where clause, and then the select clause. And it uses schema consistency guided decoding, as it calls it, which essentially is some simple heuristics that help the system avoid making errors at prediction time. And it includes some SQL syntax constraints, like, for example, since we're predicting an execution order, you cannot predict the select keyword if you have not already finished predicting the from clause and things like that. So this is a way to tackle the problem that we have discussed, that this decoder is responsible for predicting a correct syntax. And another heuristic that it uses is that all schema attributes that are going to be predicted must be from tables that appear in the from clause. And this is where predicting in execution order becomes even more useful, because we start by predicting the tables that we're going to use. So having predicted them, it is very easy to restrict the system into predicting only columns that appear in these tables. So these are some tricks, some techniques to try to avoid all the drawbacks of a sequence-based decoder. And the last system we're going to see for today is called RAT-SQL. It works on the Spider dataset. And what is very interesting is that it encodes the input as a graph, a question contextualized schema graph. So first of all, what a schema graph is a graph that it contains all tables and all columns of the schema. And it also contains all the relations between them. So it has edges that show which columns appear in which table, which columns are primary keys, or which columns are foreign keys, and so on. And then we contextualize this schema graph using the natural language question. by adding all words of the NLQ as nodes in the graph. And we can actually connect these NLQ nodes by performing schema linking. So in this example, you can see that the word department is connected to the table department using schema linking. And then these nodes are encoded using either glove or BERT. Obviously, BERT gives better results. And then RAT-SQL uses some specifically modified transformer networks that are called relation-aware transformers. And what these transformers do is that they are biased towards the edges that we have discovered and the edges that are present in the schema graph. So this is a way of adding all the information and all the relations that we have so that the system can create better SQL queries. And after having processed the input with these relation-aware transformers, RAT-SQL uses an LSTM decoder similarly to IronNet to predict an SQL query as an abstract syntax tree. So this is almost exactly the same process as IronNet, with the main difference being that RAT-SQL predicts directly an SQL query and it does not use an intermediate language. So here we can see an overview of all the systems that we have discussed. As you can see, the majority of these systems uses BERT for natural language representation, and we could argue that the two systems using GLOVE only do so because at the time that they were released, BERT was not yet available. We can see a lot of different choices when it comes to schema linking, and we can also observe that almost all systems working on the WikiSQL dataset do not bother with schema linking. We can see that the main approach for input encoding is to concatenate all the natural language query and the schema elements with some different approaches here and there, like graph encoding for RAT-SQL and separate column encoding for HydroNet. And finally, we can see that when it comes to the output of the decoder, besides some sequence-based decoders here and there, most systems working on WikiSQL use sketch-based decoders, and most systems working on the Spider dataset use grammar-based decoders. And this is obviously because they need to be able to predict much more complex queries. Finally, you can see how these systems perform and what their accuracy is. So on the WikiSQL dataset, we're doing very, very well. And some research even suggests that we have reached maximum performance, because there are also some errors on WikiSQL, and we cannot expect the system to figure these out. And we can see also that there's still a lot of room for improvement on the Spider dataset, and these scores are without counting condition values. So if we count condition values, there is even more room for improvement and for new ideas for making better text-to-SQL systems.
The text-to-SQL problem has been the holy grail for the database community for several years. And in this tutorial, we saw many different systems that employ deep learning techniques to solve the problem. So the question that naturally arises is what we have achieved, how far we have gone in the field, and how many different challenges we are able to solve if we have solved any of them actually. So the first question that arises essentially is how we evaluate the different systems in order to understand their advantages and their disadvantages. And benchmarks like WikiSQL and Spider have contributed immensely on developing new methods and employ deep learning techniques. But they focus on measuring effectiveness only based on the number of queries translated. They do not allow us to understand in depth exactly what type of queries each system can answer and what type of queries they cannot answer. WikiSQL does not have many query categories, while Spider has only 4 very basic categories of different complexity. Furthermore, current evaluations focus on effectiveness, as we already explained, but they do not consider the execution time of the translation process. And some of these methods actually use several different steps to be able to translate the query. For example, earlier we talked about the execution guided decoding, where the system tries to figure out which of the SQL queries that are generated by the system actually would generate results over the underlying database and ignore any of the possible queries that will not yield any results. So this post-processing step takes time, but this is something that current evaluations do not consider, do not measure. Then another issue with WikiSQL and Spider is that they do not allow for more than one translation for the same natural language question. And that, of course, is not always correct because the same query may be possible to have different interpretations based on the data and based on the different intent of the user. So if we really want to understand how systems work in depth, if we really want to understand their shortcomings and their advantages, and if also we want to be able to combine the best of existing techniques and move forward our research and our efforts, we really need to understand the capabilities of existing systems and approaches in depth. So in order to do this, we really need to focus our efforts on benchmarking approaches that allow us to shed more light into what current efforts have achieved. Towards this direction, the Thor query benchmark that is presented in Sigmund this year provides a rich set of queries categorized over 17 different categories and covers both keyword queries and natural language queries. And the focus of our design here was to cover different SQL challenges as well as different natural language challenges. So when we test different systems, we are able to understand where each system excels and where each system struggles to find answers, if it finds any answers at all. Now, what about the quality of the solution? And here we observe that we really don't have any universal solutions. And that is despite the fact that deep learning techniques are trained over datasets such as WikiSQL or Spider that provide queries over different domains. In reality, when we take this system and try to make them work over a new database or a new domain, these systems most of the time do not perform as well. So essentially what we see in industry, for example, is that we see domain or application-specific approaches that are tailored to work very well on a specific domain. For example, using ontologies to be able to answer natural language questions over sales data or over health-related data. For example, if we take a deep learning system and try to use it over the Sloan Digital Sky Survey dataset, I think you will have a very nice surprise because, hint, this dataset contains only numerical data. Now, what we need here is to be able to build systems that work well for different datasets. So if we are able to have a system that can work equally well on different domains, that would be an excellent achievement. What about deep learning? So today we focused on all these deep learning techniques, but should we go deep learning all the way? In fact, database approaches have been shown to generate easily semantically correct SQL queries because they are using the underlying database information. On the other hand, neural machine translation approaches promise to be able to generalize to different types of queries and data. However, we are not there yet, as we have already discussed. The promise here is how we can combine the best of both worlds. And here we see two different paths. One is to combine different techniques from the database and from deep learning world and see how each technique can be used to solve a particular problem. Another path would be to see if we can combine different systems that are able to answer different types of queries better. The next question, the next challenge that we need to think about is whether we should allow for only one answer or whether we should allow for more answers. And as we have seen, deep learning approaches assume that there is only one correct translation for a user query. But that is not always the case. For example, here we see that the user is asking for Italian restaurants, and this query is actually asked over the Yelp database. And we see two different interpretations. Both of them are correct because business can be categorized as a restaurant and Italian at the same time. But it may also be the case that we have restaurants that serve Italian but are not categorized as Italian restaurants. So essentially, how can we balance diversity and disambiguation? Early database efforts in on this problem allowed for diverse answers, trying to figure out how would be the best way to answer the user query and find what the user is looking for. And we saw that deep learning techniques are on the other, follow the other approach of just finding one best translation for a user query. Maybe we have to find the right balance between diversity and disambiguation. Now, what about answer validation? How can the user confirm that the results match the intention of the query? And this is important in several fields. For example, when you have a natural language interface helping a doctor to find information over a health database, how does a doctor make sure that the answer that the system returns is actually the answer for the query that the user wanted to ask? And here we come essentially to the inverse problem, the SQL to NL translation problem, or in other words, natural language explanations that can be for queries, but can also be over results. So how can the system describe the results that the user sees in a coherent, in a natural language format that helps the user understand the gist of the results. Last but not least, what about fact-checking? What about when the natural language query is actually a query about a fact, and we want to see whether this fact can be checked against the database and whether the database can confirm that this fact is correct or not. And what if we can repair the claim with the correct information? And then there are more challenges, how we deal with context, how we translate text to other query languages such as Sparkle, how we translate text to visualizations. Building natural language interface databases has certainly come a long way and has a long way to go. Thank you for your attention, and we are here to answer any questions you may have.